All right, let's go. I think that's enough to begin. All right, so we can look at some topics that we didn't really touch. So like the mixtures and separation, and probably acid base. All right, so in terms of mixtures and separation, um, you can be given questions about separating mixtures. So things like filtration, sublimation. So make sure that you're familiar with the methods of separation and the principle that they work behind. So for example, filtration, we know it works because if you have a suspension that has a solid in it, solid liquid suspension, then you can separate the mixture based on the difference in particle size. So the solve usually this not the solvent because it's not a solution. So usually the liquid will pass through the filter paper while the solid will remain as the residue. Alright, separating funnel is for immiscible liquids like oil and water, and they separate by density. Sublimation, you need one, well, if it's a mixture of solids, one of those solids need to be able to sublime for you to use this method. So solids that sublime are things like iodine, ammonium chloride, um, those mothballs that people put in closets and things like that, and naphthalene. Alright, we know that simple fractional distillation, evaporation, crystallization, you're all the principles are similar because they all involve heating, and typically the solvent, well, the substance with the lower boiling point will leave the mixture as a vapor, and you can, if it's the distillation methods, you can actually get back um you can get back it's usually the solvent, or get back the more volatile component by attaching the condenser to it, and you can get back your, so if it's a mixture of say ethanol and water, that would be fractional distillation. Since it's two liquids, you can get back the alcohol. Since alcohol, the ethanol has a lower boiling point than water, you can get it back. Alright, and then the sugarcane, the extraction of sugar from sugarcane is just a method or an application of the mixtures of separation. So different techniques are used to separate the sugar from the sugarcane. So there's things like filtration, evaporation, centrifugation. All of those are separation techniques. Alright. Solubility though it's another thing that can be tested. So It's usually number will appear number one if you get a solubility curve. So you should know how to interpret the solubility curve and how the solubility curve is affected by temperature, or the solubility is affected by temperature. So some substances are influenced more, or the solubility change or varies more with temperature. So like in the diagram here where potassium nitrate sees a much greater change when you increase the temperature than sodium chloride. Sodium chloride looks like a straight line, but it's very small, so it's like it's stuck at the 20 gram of sodium chloride in 100 grams of water. All right, so yeah, so let me see. You can do the first one. Hmm. So it's ionic. So, alright. So you have to. I'm gonna hear mention about potassium nitrate though in terms of, right. So therefore it is what. So the same descriptions that you use for water and for pentane, we can use it for potassium nitrate too. So so what did you say about the pentane? Yeah, and what did they say? And they said water was what? Yeah, so what is potassium nitrate? Yeah, so but I'm saying how would you describe it? So you just describe pentane and water, where you can use the same labels for potassium nitrate too, the ionic substance. So which category would it belong? Yes, so why did you bring up the fact that it was polar or non-polar, the solvent? If it's polar, or non-polar, potassium nitrate. So you have to describe the potassium nitrate as well. So it's also polar, right? So it is good that you mentioned that water is a polar solvent and that pentane is a non-polar solvent, so that's good. But you have to now relate it to the solute as well. Alright, so like dissolves like. So that's a rule, that's a general rule for um interact when we're interacting or when solute and solvent interact. So yeah, so mention the polarity. So that's what I was looking for you to add to your response. Alright, so the response was good, but I just wanted you to mention that it is polar. Potassium nitrate is polar. Yeah. Alright. So the next aspect is graph. So you would have to look at these things, and I trust that you are able to read these things. Let me see. Um, so alright. So let me do can I say that? Alright, so this says determine how the solubility of potassium nitrate varies with temperature. So using a graph. So let's say, so we didn't do the graph, so but let's say it looked like, as there was that image earlier. So let's use that image from earlier. So so let's say when it did the graph, it actually looks something similar to this. So you get a curve looking like this. How would you describe um what's the question again? Forget the question already. To describe how the solubility of potassium nitrate varies with temperature. Alright, so how does the solubility of potassium nitrate vary with temperature? If it looked similar to this. So when you plot a graph, you ended up with something looking like this. What would you say about it? Yeah. No, can't say directly proportional. So KNO3 we're looking at it now, not the. Mm-mm. So don't use the term directly proportional if it's not a straight line. So yeah, straight line is that's the only time you can use the terms directly proportional or inversely proportional. It has to be straight. Yes, you can say that. All right, so that's one thing. Um, so you can talk about the extent. You can talk about the extent now. What else can you say about it? Look at the shape and all that. The higher the temperature gets. Uh, I think you can reword that a bit because look at this one. This one actually has two lines on it. So if you were if you were comparing these two, what's the difference? Because the sodium chloride line is going up. So if you look at the sodium chloride line, it is going up with temperature as well. But what's the how would you make a distinction in how you describe how they change with temperature? Right, so something like that. So you can talk about that like as the temperature increases, that the solubility um or the amount of potassium nitrate that dissolves increases greatly, or there's a significant increase. So we just want to get a sense that the change is very significant. So you get a curve going up like that. So I wanted to mention that. It was on page 202. Check back on the let's check it's January. Alright, so I'm going to show you since we didn't plot the graph, I'm going to show you the same graph. But before that, let me just alright, so that was fine. Alright, let me go back to the graph. So determine the solubility in grams per 100 cm³ of potassium nitrate at 65 degrees Celsius. So let's see if we can get an estimate. So 65 degrees Celsius. Let's see if we can get an estimate from the graph that we have on this. So at 65, 110. Yeah, so it looks like yeah, so the first time, so about 120. So we can use that. All right, so 120 grams per 100 grams of water or cm³ of water. Two. And then they want to know to, which is pretty common for them to ask on a solubility question. Using your answer in C2, which would be the 120, calculate the mass of potassium nitrate that will be precipitated out from the solution if the solution is then cooled down to 35 degrees Celsius. Alright, so we need to look back at that. So it's cooled down to 35 degrees Celsius. So 35 will be between the 30 and 40. $52. I'll just say 50 and then let me see. So and the because alright, so the y-axis goes up by how much though? 40. Well, each line goes up by 20. So far it's between 40 and 60. So alright. So how much will be precipitated? So if at 35 it's 50, how much would be precipitated of the potassium nitrate will be precipitated if you cool it down from 65 to 35 degrees. So solubility at solubility at 35. So the solubility at 65 was 110, 120, 120 was 120. grams per 100 grams, and the solubility at 35, so it was 50. So how much will be precipitated out now if you cool the solution from 65 degrees to 35 degrees? Mhm. All we have to do is just take the difference because at 65, so whatever you see on the solubility curve represents the maximum amount that solution can hold. So at 65, the maximum amount of solid or the maximum mass of solute that can be held in the solvent is 120 and the maximum at 35 is 50. So if you have 120 initially dissolved in the solution, when you cool it, solubility is going to drop. So it's just going to be spitting out the excess or releasing the excess. So the excess will come out as a solid, or we can say it will precipitate out. So if they're asking you to determine the amount that will be precipitated out, you'd have to look at the solubilities at the different temperatures and just subtract. Alright, so that's how you determine how much will we precipitate out. Alright, so if we do the difference of those two, that should give us what? What's the mass that will be precipitated out? So 770 grams per 100 grams of water. Alright, so that's how, so you just subtract both. Alright, but the question next, I think is the next question had an interesting kind of spin on it now. So it's asking you to calculate the concentration of a saturated solution of potassium nitrate at 35 degrees. So they want the concentration in mole per dm cube, and you see they give you some we call it some constants, So they're giving you a hint as to what you should be doing. So why did they give you those values? What do you think they gave? Okay, so we can find the molar mass of potassium nitrate. So determine what the molar mass of potassium nitrate is then. 100 and how much? 1 grams per mole. Alright, and what would we do with that molar mass? So 0.5 moles. Alright, but note though that this moles though is in a certain volume. That mole was in the volume. What volume? So, as remember, the solubility, look at the solubility value. You say it was 50. It wasn't just 50. And there's a reason, yeah. Or 100 grams would be the same thing as saying in 100. So that's, yeah. So one gram of water is equivalent to one same cube of water. Yeah. So that means the mole that we just found is the amount in a 100 cm cube. That's it. That's it. The mole that we just found is the amount in 100. So how would you find the concentration then? Molar concentration in dm cube times up. You get it times up by 10 times to get the concentration. Hmm. Okay. All right. So there are different approaches you can take. So you can say if there's 0.5 in 100, you can use a relationship to say how much would be in 1,000. So yes, you can do that. I could just plug it in the formula. Um, molar concentration is equal to the number of moles over volume. So if you take that approach as well, that's fine. So the moles would be 0.5 and the volume that it's dissolved in we just convert that to dm cube. So we could convert the 100 to dm cube, 0.1 dm cube. Alright, so both ways should give you the same answer. Alright. So probably it's unexpected with the way they ask that one, but it is valid. Sugarcane, wait. So, so remember, sugarcane is a part of mixtures and separation, the different phases. Um, pure substance mixtures. So a mixture is made up of more than one substance. So it's a combination of more than one substance. All right, so they're combined by physical means. All right, so and it means that they can be separated. A pure substance is only made up of one type of particle.